Awesome. Okay, so let's get started. So today we're going to continue off policy RL, kind of get into the weeds of it a little more, prove some things, and then try to make this practical into algorithms that you'd actually use, like non-factor predict. And so what we're going to do today is start from where we were last time, motivate the Bellman equation, and like build up from there the practical off policy algorithm that you can use on a robot, right? And so that's going to be our roadmap for today. So let's just do a quick recap of where we are in the class. We've started through policy grid. Today, hopefully, we'll finish up approximate dynamic programming. Next class, we'll get a model-based RL. And then we'll try to unify these things into a coherent framework, right? And so let's start a few concepts ago. We're thinking about why policy gradient is inefficient, right? And we said that, okay, it's inefficient for two reasons. One, because it's on policy, it's not able to use past data, just related batch. And second is the high variance estimator, right? And so what we wanted to do to make on policy RL efficient enough for things like robot is we want to lower the variance and we want to use an off policy RL algorithm that can use past data, right? And so those are the two ideas we really want to get at, lowering variance and going off. And so the first thing we did is we said, what can we do to lower variance? Well, we really want to get objectives like this, which average across many different future runs rather than just a single one. But we're in a continuous space, so it's hard to do that. And so what we're going to do is use the magic of function approximation. So we're going to try and learn a model with a parametric function approximator, which approximates the future outcomes, right? And that's going to help us lower variance because it can share information across this, and this state, even if they're not exactly the same. Right? So policy gradient was a single sample estimator, so that's high variance. We want to lower the variance. So we want to average our return estimate. We'll never get back to the same thing. So we use function approximation to get an average return estimate, right? And so that's the key idea behind actor critic methods is we want to use function approximation to lower it. Okay, so the two things that we need to like remember as notation were Q functions, right? The Q functions are expected sum of rewards in the future under your policy phi, starting from state ST, taking action AT, and then following the policy phi thereafter, right? So it's telling you how good is an action AT to take at this state ST if I follow the policy phi after the first step. So that's what a Q function is. And a value function is the same thing, but not taking that first action separately, just saying, if you start at state ST and take the first action according to your policy, and then continue taking your policy thereafter, it's telling you how good is your policy phi at state ST. And we saw that the value function is nothing but the expected. So under your policy, if you take the expectation of your Q function under your policy, that gives you your value function. Right? And the logic is just take this thing. This is choosing for a particular A. You just average over all possible A's. That's going to give you, as if you started at S and then took actions according to phi. Right? And so your value function is your expected Q function. In lots of RL textbooks, you will see Q star and B star. Those are optimal. We'll get to those in a second. But right now, we're doing Q phi and B phi, which means there's a Q functions for a particular policy. That policy may not be optimal. It's just evaluating how good is a particular policy. Right? And so this is policy evaluation. And these are like, we haven't talked about how to get these yet, but these are the definitions of the entities we want to get. Right? And the point is that if we can get these things, they kind of try to approximate this sum of rewards in the future. So they lower variance. Right? Okay. So attempt 0 was we wanted to do Monte Carlo estimation of Q function. So we said, let's just take a bunch of state action pairs, right? And let's just try to regress from state action pair to the sum of rewards in the future under our current policy. So we're just going to do Monte Carlo simulation and then just solve a big regression problem to go from state of action to the future sum of rewards, right? What is the issue with this? Like, we're just going to take a bunch of samples and we're just going to like regress from S and A to the sum of rewards. This is still on policy. Still on policy, perfect. And there's another issue with it. High variance, right? So if we go back to the two things that we really wanted, we want low variance and off policy. This does neither, so it's trash, right? Never do Monte Carlo anything. But it's a good thing to think about, right? So you want to have something, it's unbiased, but it's going to be high variance and it's going to be on policy. Right? And so attempt 0 is not great. In attempt 1, yeah. Because you sum up a bunch of random variables, like you're just sampling across the whole horizon. And so you're not using any function approximation besides like it's like you're wiggling every single time step. And you're trying to model a random variable, which is the sum of every random variable. So it's not structure. Yeah, it's not taking exactly. Okay, so that was attempt 0, Monte Carlo Q estimation, right? And now we say, yeah, we're in a Markovian setting. We want to use some temporal structure to this problem to kind of do better better, Q estimation, so that we can reduce the variance of policy grade. And so we started from a value function. We said that's the value function. And then we use this recursive nature of your value function. And so the way we derived it, we said that the sum of rewards is the reward at the first time step plus sum of rewards every time step thereafter, right? You can move the expectation inside and say this is the sum of rewards plus the expectation of the sum of rewards in the future, right? And that allows you to say that your V pi is the expected R plus V pi in the future.
Here, when you move the expectation, is there a reason why you keep the expectation outside as well?
Like because 80 depends on that, right? Yeah. That's always the danger of doing shorthand expectations. But really, this expectation is over 80 sample from pi and ST plus 1 sample. So the 80 sample from pi stays here and everything else converts. Right? Good. So, yeah. Oh, because when you're going to rewards in the future, they don't depend on past. And so, like the rewards from time step ST plus 1 onwards don't depend on the past, so you can draw it. Okay. So the recursion you get, which is what we call the Bellman equation, is saying that your V pi ST is equal to the expectation under pi theta of R of STAT plus V pi at the next time step, right? And so this holds that convergence, right? If you have the optimal V pi, right, or not the optimal, you've like approximated V pi perfectly, then this has to hold, right? And so we still haven't got to an algorithm that can compute it. This is just saying there's a condition that needs to hold when like for the perfect V pi. Yeah. And so what we need to figure out is how to go from this, how to use this condition to go to an algorithm that we can. So the main point of the Bellman equation is that this equation holds for V pi when it's perfect. We need to go to an algorithm that we can apply iteratively to kind of get to V pi. Yeah. The whole point of doing this though is that this will allow us to not just do Monte Carlo estimation where we sum up over all the time steps, but do something that's lower variance. And so the way we did it is we described this like iterative procedure where you construct targets, right? So you construct targets by saying you're going to like take your current reward, you're going to add your value estimate, right, at the next time step. You're going to construct that as a target and then like treat this as a number and then try to do regression onto that number, right? And then you're going to get a V and then you're going to construct a new set of targets and they're going to do regression again, right? And so essentially you'll construct a set of targets, do regression, construct a new set of targets, do regression, construct a new set of targets, do regression, repeat, right? And we'll show that in how in many cases that will, or some cases that'll converge to the V pi which satisfies the equation. And so, but mechanistically, the way you want to think about this is that it's going to like go through a procedure like this, which is saying that you're going to run many steps of this iterative loop. So you're going to say you start with some V, you're going to construct targets, do regression, construct new targets, do regression, construct new targets, do regression. You're going to run through many steps of policy evaluation. So this step is what you'd call policy evaluation, right? And this step is what you'd call policy improvement. And so in policy evaluation, you do this like repeatedly, yeah, till you get to a V pi that you're happy with. And then you can use the V pi in order to update your policy. after which you have to redo policy evaluation, right? And so the point here is that you can think of this as telling you, this V pi is telling you how good is the policy pi at state S. And you can think of this thing as trying to use that estimate in order to lower variance of the gradient, right? And so we'll get into the details of why this thing converges in a second. But any question?
We're gonna iterate through the of that.
So the point is that this thing, right? This thing will converge to a value, like we're going to show that this thing converges to like the true V pi, right? Or like at least in tabular settings, right? So it's going to converge to the true V pi, and the V pi is really an estimate of how good something is, right? And so the point is that that recursive equation that we defined, right? Like this procedure of setting targets, regressing is going to converge that V. The final V value is going to be this. And this is going to tell us how good is that policy from state S. Right? And if you could tell how good a policy is from state S, then policy improvement is kind of intuitive, right? It says that you can take your reward at your current time step, and then normally what you really want is to be able to like have a bunch of steps in the future, right? What V will tell us is it like averages out all of these and tells us how good is A when you follow policy pi in the future, right? Well, in a tabular setting, you know that this will, you show that this converges to be pi, like the true, like if you, like we're just trying to find an attractable way to approximate this thing, right? So when you say how good something is, right, we're just like, I'm just saying the V is the goodness. And this thing is just telling you how good is the policy pi when applied at state S. Now, there's two different things, right? One of them is how good is the policy pi, and the second one is how good is your approximation, right? So you're saying that like, if I knew how to approximate this perfectly, then this would be how good a policy pi is, right? And we're saying that our like iterative procedure will give us. The second thing is how good is our estimate of V pi, and our estimate of V pi depends on like the pathologies of neural network traces. Okay? And so I don't know if I have a great answer to that. I think that's still an open question, but in principle, at least for tabular settings, this procedure I mentioned, or maybe like for linear function approximation, you can show that this converges to V pi. And V pi is an accurate estimate of how good policy pi is at state S. Right? So the point is that this procedure will actually give us V pi. And if you know V pi, then you can do policy improvement that way. Yes? So the way to think about it is Monte Carlo estimation, like tries to sum up everything this way, right? And just like regress everything. What this like TD error we've talked about right now does is it takes one step and then uses function approximation to like approximate the next step, right? So it doesn't have to sum up every single step. And so it's going to reduce variance. Okay. And so you're going to repeat this procedure. Right? So now what might be the problems with this kind of thing? On policy. Yeah, it's on policy. But it should lower variance, right? But it's on policy. The other problem with this thing is that if your policy evaluation procedure doesn't converge perfectly, like you're saying, like your estimate is going to be biased, right? And so if you converge policy evaluation till convergence, as in you run this a million times, V is perfect, your policy improvement will be correct, right? But if your V is like approximate, then this thing will be potentially wrong. And so you might have bias that comes in, and that kind of motivates this like this idea of generalized advantage estimation, right? And generalized advantage estimation says, hey, this thing, if your V is perfect, this thing is perfect, but if your V is wrong, this is biased. And this thing is pushing out the V all the way to the end, right? So the bias of V doesn't show up as much. And so this is like the Monte Carlo single sample estimator we had in policy gradient. This is the bootstrapping update we just discussed. This is lower variance bias. That is higher variance unbiased, right? And so so what they do is then sum these up geometrically, where lambda chooses how much you focus on one particular. Right? So the point is that this is like bias, but lower variance. And this is high variance, but lower bias, right? And your lambda parameter lets you choose between them. Right, so if you ever see ideas like eligibility traces and stuff like that, like all of them kind of have this idea. And so if you look through the Sutton and Bartow book, you'll see a whole chapter on eligibility traces. And all that it's doing is just trying to sum up these different estimators. Yeah.
What does it mean by bias?
Bias is that if your V is wrong, then in expectation, this estimator is not going to give you like the true sum of rewards in the future. Right. So like your estimator does not converge necessarily to the true sum of rewards in the future, right? Because you've approximated with the wrong V. So you're going to take one step and then you've like stuck in an approximation. That approximation is wrong, then your overall thing is wrong. Whereas that thing is literally taking the sum of rewards, right? And so there's no approximation. Okay, yeah.
And this geometric sum would replace what term in the policy gradient exactly?
The Q term. So whenever you have policy gradient, you can have Q or you can have Q minus V, right? Which is what you'll call advantage, where V is your baseline, right? It's just going to like, you're going to replace that term. Like normally we just, in policy gradient, we compute it with like sum of rewards from now till the future. In this bootstrapping error, we say you use R plus V minus V.
So you replace that.
You replace that thing by this geometric sum. Right, so in policy gradient, you use some R. In this thing, use R plus gamma V minus V. And then the generalized advantage estimator uses some like geometric sum to replace this term. Right? The thing that multiplies your log probability. Okay, does that make sense? And so, popular algorithms that you'll see that kind of do this is called A2C or A3C, which tries to use an update like that. Asymmetric advantage actor critic, right? And so, or asynchronous advantage. I think it like basically tries to do an update like this, but just with lots of parallel focus, right? And so that like often works really well. Okay, so the issue here, does that make sense overall as a paradigm? Like the main point we use is that we use the recursive nature of the value function to define this Bellman update. And then we define this recursive procedure, which says construct targets, regress, construct targets, regress, construct targets, regress. And we said that that's going to like replace the sum of rewards in our value function, sum of rewards in our policy grade. That's going to lower the difference. Right? That's the main point we come. Okay, everyone with me? Awesome. Okay, so the issue here is that it's still on policy, right? So we said we want something that lowers the variance, but we want something that's on policy. And so what we want to figure out next is we want to figure out how to go from here to things that are off policy. So that we've talked about things that are on policy. We want to go to things that are off policy. Then we want to like, this is not what you do in practice. And so you do a bunch of tricks in practice. And we want to talk about those tricks and why they make sense. And then we'll talk about like what our open problems and off policy are. Yep. And so the main focus of today is going to be going from these on policy updates to off policy and like then talking about the tricks that make these things work. I don't know if they're tricks, but techniques. Okay. Okay, so before we get into off policy things, it's useful to take a closer look at this value Bellman equation, right? So we said that the value Bellman equation was V pi is equal to expectation pi of R plus V pi in the future, and this whole that convergence. And then I told you that we're going to do this like procedure that looks like this, the Bellman update. And the Bellman update is kind of this like iterative procedure where we're going to like keep iterating between constructing targets, regressing constructing targets. So like a natural thing to wonder is like, is this the gradient of any objective, right? Is this like gradient descent? So it's important to think about this thing. Like you're actually, what you're doing is you're like constantly changing the objective, right? So you're saying that I'm going to construct some targets. I'm going to like regress those targets, and then I'm going to construct new targets, and then I'm going to regress those targets. I'm going to construct new targets and regress those targets, right? And so you can actually show that this is not the gradient of any well-formulated objective, right? It's an algorithm which is called fixed point iteration, right? So it's not actually doing gradient descent on a single objective. It's instead trying to like repeatedly apply a function over and over, right? So a fixed point iteration algorithm is saying if you have some update to f, you're going to like take your xn and you're going to repeatedly keep applying f to it. Right? So in our case, f is going to be constructing targets and doing regression, constructing targets and doing regression. Right? So you're going to say like you had your initial set of values, v, and then you're going to like apply this procedure, which is going to be our f, which is constructing targets and doing regression, right? That is our f. And that takes us from vi to like vi plus 1. Right? And so we're going to repeatedly apply this procedure. And it's I want to emphasize that it looks like gradient descent, but it's not. Right? So it's like it's an instance of this fixed point iteration algorithm where you're going to like keep applying this projected Bellman update, which is saying you're going to take your previous value functions, construct targets, regress. That's going to give you a new value function. And then you're going to repeatedly apply that same procedure over and over and over again. Does that make sense? Right. So this is a procedure which is called fixed point iteration. And you want to find the fixed point of your fixed point iteration algorithm, right? Which means you want to find the x star at which it converges, right? And because we know that this thing holds at convergence, right? We know that we know that like at convergence, this like if you replace x star by v5, like this thing will fit, right? And so you know that if you treat f as your projected Bellman operator, then v pi, like f of v pi is equal to v pi. You know that's true, right? So if you have the true v pi, like v pi perfect, you know that f of v pi perfect is equal to v pi perfect, just by the definition of it, right? That is like literally the Bellman. So what we need to show is that this iterative procedure will get xn, where n tends to infinity, to be equal to v pi, right? Yeah. So this is in like these are this is going to be in function space. So you can think of xn as not like a state. So you can think of xn as like a value function. And you can think of f as your Bellman update. And this is going to be like vi plus 1. And then what you want to show is that like this is a function, and you want to show that that function converges to the optimal function, not that the like state converges to the same state, right? So like even at v pi, like v pi s is not going to be equal to v pi s prime, but you want to show that like you know that this basically here you know that this holds on the left and the right, and so you want to show that this iterative procedure converges to like this. Like it's important to remember that x here is not a state, but x is a value function. And f is the procedure of Bellman projection, right? And we want to show that that thing converges. And it converges to the optimal function. So we want Vn as n tends to infinity to be equal to v pi, the true v pi. N is the number of iterations of this procedure that we repeat. So we're saying that we're going to repeat this procedure. Each of that iterates one n, right? And so you can think of this as like this procedure will start with some v0. Then you like construct targets, regress, construct targets, regress. And that's going to give you a v1, a v2, etc. till vn, right? And you want to show that that becomes v pi at convergence, right? Yeah.
Then we take one gradient step and then do the same thing again, or do we take multiple gradient steps?
You take multiple gradient steps.
Yeah.
So you take multiple gradient steps over here, but every so often you have to like change your practice. It's a good question. Right, so the way that you'd actually do this is you construct some targets, take multiple gradient steps or like k steps, right? and then you like change your targets again, and you repeat, right? And we'll go over that more in our like practical section. Okay, but let's go through a little bit of math to show that there's this update, like does our fixed point iteration update converge to the true value? Like, does it converge to V pi, right? So we started at V naught, just some random function, and we repeatedly apply this procedure. Does it converge to the true value function, right? And so we're going to try and prove that. So it's important to remember that this is not a gradient descent objective. This is like, you do gradient descent for a while, and you change your problem. Then you do gradient descent for a while and change your problem. And so this is really a fixed point iteration. Yeah. Okay. Okay. So the question is, does this convert to the true value as a fixed point? So we're going to use this Banach's fixed point here, which says that if you have a metric space with a norm D or some distance metric D, right? You want to show that if you have some function f, which is a contraction, that repeatedly applying f is going to convert, there exists a fixed point, and that fixed point is unique, right? Which means that like, what this is saying is that if I have some x and I have some y, which are just two elements, right? So in our case, x and y are going to be like two value functions, right? So let's call it like vi and ui. We're two different candidates for a value function. If we apply the Bellman backup to them, so this one becomes vi plus 1. This one becomes ui plus 1. If we can show that the distance between vi plus 1 and ui plus 1 is less than or equal to some q times the distance between vi and ui, then you can show that you can show that f is a contraction. So you're saying that like x and y, when projected through this function f to the next iterate, are closer together than x and y were originally, where q is less than 1. They're just like two candidate value functions, right? And so what we want to show, what this suggests is that, so x is vi and y is ui. They're just two candidate value functions, and f is your Bellman backup, right? And so what we want to show is that the Bellman backup moves vi to some new vi plus 1, moves ui to some new ui plus 1, and now vi plus 1 and ui plus 1 are closer than vi and ui were, right? And you can essentially show that basically if everything keeps getting closer, then it'll converge to a single point, right? So we're not going to go over the proof of this, but we're going to use this to prove that our value function is convergent. And so, sorry, this is a little bit confusing, but what we're going to do is we're going to like consider a tabular version of this update. So we're going to say that we had some v pi I, right? So we're going to say v pi I is going to be backed up into v pi I plus 1 this way, right? So you have like, you can think of this as like it's like a vector, right? It's a state dimensional vector, right? Where each of these, you have like k different entries, where k is the size of your state space, each of which corresponds to the value at iteration I at different states, yeah? And then your Bellman backup is going to apply, sorry, there. Okay, it's going to apply this kind of procedure, and it's going to get a similar s-dimensional vector at vi plus 1 through this procedure, right? So you're going to say, I had a vector values, which was vi. Jesus Christ. I had a set of values, which is vi. I'm going to apply this procedure, and it's going to give me a set of values for vi plus 1, right? And that is going to be our like overall like procedure for doing one fixed point iteration step. And what we need to show is that this procedure gives me something that's a contraction. Yes. So going back to our, sorry. The distance between functions. So we're going to use a norm. So we're going to use an infinity norm. So we'll go over this in more detail, but at a high level, like you want to think of like vi plus 1 pi as a big vector, a state dimensional vector. You want to think of vi pi as a big state dimensional vector, right? And you want to show that like applying, you can think of this procedure as your f, this whole procedure that maps from this vector to this vector as your f, and you want to show that that procedure is a contraction, right? Because if you can show that that procedure is a contraction, you can show that vi tending to infinity is going to be equal to the fixed point psi.
Yeah, sorry, why is the result of the value function a vector and not a scalar?
The value function is a vector, like the v pi s is a scalar, as in like you map s to a scalar, but there's like 1,000 s's in your state space. So you can just think of it as like a vector where each entry is the value function for each particular state, right? And so it's just a big vector where this is state 0, this is state 1, this is state 2, and this is like its scalar value, right? So it's a vector because like each entry is a scalar value for every state. Right? Yeah. For this, we're gonna sort of tabular this. Okay. And so for shorthand, we'll call this procedure, which maps from this vector to this vector as BP pi, right? There's a Bellman, you can call it your Bellman backup under dynamics P and policy pi, right? So you can see that this backup depends on policy pi and dynamics P, right? So it's saying that you take these things, you project it using some dynamics P and policy, right? So the Bellman error will be different under different policies and different dynamics. But in this case, you're going to keep the dynamics the same, you're going to keep the policy the same, you're going to repeat the same procedure over and over and over again, under the same policy, under the same dynamics. Yeah.
Because the middle notation, it should also be vi plus 1 pi.
Yes. Thank you. That should be fine.
Are you just doing it over a bunch of rollouts?
So right now we're just gonna try and prove it in the tabular setting, which means that you like have a big vector, you can analytically compute it. You can take complete sums over it. But in practice, you would do it with rollouts. Okay, so to repeat what we're trying to do, we're trying to say that if you have, we're going to treat f as our Bellman backup, we're going to treat y and x as different value functions, and we're going to try and show that they contract. If they contract, they'll converge to be flat. By 6.2. Yes.
Did you have a settings that? So it's the top like update description. Is the update that you described this like?
It's like one step of it. So you can think of it as like, so this step is a different step. Like the thing where you're doing the regression is something we'll call a projection. We'll get to that. What we're doing right now is we're just following this step. So what we're saying is that we have like some value functions, right? And you're like dumping them into like a new set of value functions. And then you're like repeating this procedure, right? So you're going from V to a new set of backed up V. And then you like repeat this procedure. Backed up V, repeat this procedure. We'll talk about how to project it into like this kind of thing after, right? But right now what we're doing is something purely tabular. Right, so we're saying we have just like a table of values. So like, forget about the first line for a second. Just think about the second line. Right, you're saying VI and call this VI plus 1. Right, so you're going VI to VI plus 1, and then you stick the other thing into the right-hand side. You do put the VI plus 2 and repeat. Okay, so let's keep going. So what we want to do is we want to prove that BP pi is a contraction. Okay, so the way we're going to do this is we want to show that this dfx fy is less than or equal to q dxy, right? So when you pass x and y through the f, they get closer than they were originally, right? We're just going to instantiate d, f, x, and y in our setting, and then we'll show that this works. Yeah. Okay, so f is our Bellman operator, right? So it's going to be our BP pi, like we just talked about, right? So Bellman operator BP pi, which is the same thing as like this operator, right? That is what our f is going to be. Okay. This is going to be a little confusing, but I think we'll make it through. Please feel free to ask me any questions in between. D is going to be our infinity norm, right? So if I have like two vectors, the infinity norm, so if I have like vector A and vector B, the infinity norm, and let's say they have like elements I, right? The infinity norm is going to be the max over I of the absolute value between AI and BI, right? So it's like trying to find, take the absolute difference between two vectors and choose the biggest one. That's the infinity norm, right? And so we're going to use our infinity norm as our distance metric. And then we're going to use X and Y as two different value functions, right? So remember, they're going to be two different value functions, which means that like, let's call X like let's call X VI pi, and let's call Y UI pi, right? They're just like two different value functions. And so there, you can think of them as like two different vectors, right? Which are like candidate value functions. And we're going to apply this operator, which takes us from this one vector to a backed up vector. We're going to apply it to VI pi, and we're going to apply it to UI pi, and then we're going to show that they get closer, right? So it's easier to think about these as vectors. You can think of this as a big vector. You can think of this as a big vector, vector, vector. And this is just like some operation that maps from this vector to this vector, right? And we want to show that after this operation, VI plus 1 and UI plus 1 are closer than VI and UI were in terms of the infinity norm, right? Which means that the largest difference between them is now small. Yes? Yes.
I is number of trajectories, right?
I is the number of iterations of this. So like I is not number of trajectories. Basically, you're going to start at like V0, which is your initial guess at your value function. Okay. Then you're going to apply BP pi V0 to it, which is going to give us V1. Then V1, you're going to apply BP pi V1 to give us V2. Right? You're going to apply. So VI is the number of steps at which number of iterations of running this procedure. Right? So you can think that every time you do that, you take that and convert it into a different vector. That's one. You just keep increasing that I over and over. And so mapping it back to like what we did practically, right? Like in the update here, it's like saying you construct targets, you do regression. You construct targets, you do regression. It's like the number of steps of that like repeated procedure that you've done. Constructing targets. Okay, so does the objective make sense? What we want to do? We want to show that the infinity norm between VI plus 1 and UI plus 1 is less than or equal to some gamma between the infinity norm times the infinity norm of VI minus UI. Right? So you're trying to say that like if you apply the Bellman operator for any two VIs and UIs, right, they get closer in infinity norm by some factor gamma, which is less than. Right? Okay, any questions? Yeah. It does, but I think you can show that it converges under any distance function. Yeah.
Why did you choose gamma here to be the Q? Or this gamma is the same, the very same. Right now, are we just like ignoring that and say?
Well, so far I haven't used the gamma, but we should stick in a gamma. There should be a gamma like right here. It'll show up in our derivation, but it can be anything that's less than 1. Okay, so let's just start working through the steps one by one. It's going to be a little bit involved, but we'll zoom out and say. Yeah. Okay, so we have VI plus 1, UI plus 1. These are two vectors, right? So you're trying to take the infinity norm, which means that if you have two vectors and you take their infinity norm, you like subtract them, take the absolute value, and then choose the entry that has like the highest absolute difference, right? And so you can write it as max over S of VI plus 1S minus UI plus 1S, where S is like the choice of entry, right? Okay, so now help me expand this, right? Like we know what VI plus 1 and UI plus 1. Okay, let me expand it and you do the next step. We know that VI plus 1 and UI plus 1 are expanded according to that update over on the top, right? So let's try and write out each of those, right? So you said VI plus 1 is going to be equal to the expectation under the dynamics, under the policy of R plus VI, right? And so like this thing is, yeah, okay. this thing is basically the same as like the backup over here, right? You're saying it's the expectation under your policy, under your dynamics of the reward plus gamma times UI. Right? In the same way for B, it's going to be expectation under your policy, under your dynamics of your reward plus gamma. I switched the order of UI and GI. Doesn't really matter. It's absolute value. But the point is that all we did is we expanded these two according to the definition of the backup, this thing, which is exactly that. So all we did is we expanded the Bellman backup. Yes? Just to make sure everyone's with me, we're just trying to show that this thing is a contraction. So we're trying to show this thing is true. To show this thing is true, we wrote the definition of the infinity norm, and then we expanded what VI plus 1 and UI plus 1. Yes? Okay. So what do we do next? Cancel out the work. Perfect. So you can see that these are like expectations under the same thing, like DSDA. So you can like put them into one integral. And then you can see that reward is in both terms, right? So you can just like cancel it out. And so what you should get is something that looks like this, right? You can show that like you write out this whole sum. Like basically this term and this term cancel out, right? And then gamma is common across everything. So you can take gamma outside the max. There's also a positive number, right? So you have now an integral over pi, an integral over dynamics of ui s prime minus vi s prime. Yes? Okay. What do we do next? Yeah. This is just the expectation, but we need to show a contraction, right? So let's what we can show is this next step is saying that ui s prime minus vi s prime, right, is less than the max of ui s prime minus vi s prime over all s's, right? So if you have like two vectors and you like subtract them, right, you can show that their like difference is less than the max of like, it should be absolute value. Max of the absolute value of the difference between them, right? So you have two vectors and you're saying subtract them. Just by definition of the infinity norm, you can say that like every difference is going to be less than the max difference. Right? So if you just have two vectors, subtract them, they're obviously less than the max of all the differences. Right? And so what you can do is you can say that this difference, UIS prime minus VIS prime, you can say it's less than or equal to the max of UIX minus VIX over all x. Okay? So you take these two vectors, you subtract them, you say it's less than or equal to the max difference between. Yes? So let's say you had infinity norm here, or you had an absolute value here. Now, like, what is this thing? It's the infinity norm, right? And so you can say that this is just the infinity norm between VI and UI, right? So all that we did here is we said reward cancels. And then we said that UI S prime minus VI S prime, which is basically entry-wise differences between VI and UI, is less than or equal to the max absolute value of the differences between them, right? And then you can just simplify this a little further. Clearly, this doesn't depend on S. This is the max value, so you can take it outside. If it gets to 1, right? And so you can show that this is, you can move this outside here. And again, this doesn't depend on X, so you can move this outside here again. Right? And so you can show that VI plus 1 minus UI plus 1 is less than or equal to gamma times the max of UI minus VI, which is basically gamma times the infinity norm between VI and UI, right? So let's just go through it step by step, make sure everyone follows, right? So what we did is we said VI plus 1 and UI plus 1 are defined as the Bellman backups on VI and UI, where the Bellman backup is defined as such. Yes? Now we said, let's try to say that the infinity norm between VI plus 1 and UI plus 1 is less than or equal to gamma times the infinity norm between VI and UI. So we just expanded VI plus 1 and UI plus 1. This is just the Bellman backup, right? And we said, we're going to cancel out reward. And then we're going to say that the difference between any two elements is less than or equal to the max of the absolute difference between them. And then the max of the absolute difference between them doesn't depend on anything, so it can go all the way out, right? And everything else integrates to 1. And so you can get is less than or equal to gamma times the max difference between these elements, right? And so you can show now that vi plus 1 minus ui plus 1 infinity norm is less than or equal to gamma times vi minus ui infinity norm, right? And so what that suggests is that you're contracting every time you do this update. If gamma is less than, so you never use gamma more than. If you're using gamma, gamma is going to show up here. Gamma will always be less than. Yes.
How do I show that? L, we use L infinity. Like L, I don't know.
I haven't worked out other norms, so I'm not going to comment, but like I can try sending you something. Yeah. But this definitely holds for the infinity.
So
Yeah.
here the contraction part is mainly because of the gamma. Picking to be less.
Basically, the Bellman update doesn't really work in the infinite horizon case without a gamma.
Yeah.
And so it's not. And so the whole point of this exercise, like we went into the details, but I think is a useful thing to know, is just to show that this procedure of like repeatedly doing this Bellman backup is going to get you to the optimum. And like the interesting thing is you could start anywhere and it'll get you to the optimum. Right. And so it's saying that like because of the contraction, like you have a unique fixed point and repeating this procedure over and over and over will always get you to the optimum when you're in a tabular setting. Like if you're in a table setting, it gets you to the optimum, right? So everything is countable, everything's in a table setting, you're great, and this gets you to the optimum. Which is kind of cool because it's like, this is like a procedure, which is like, it's not a gradient of anything. It's like this fixed point iteration procedure, but it converges to the. Okay, so the whole point of this was, do we like, is your name Will? Will, right? Yes. So as Will was saying before, like I've been talking to you guys about this, like this find targets, regress, find targets, regress, find targets, regress. And then we like worked out a bunch of stuff for tables, right? So like how do these things connect to each other? And so the question we need to ask is like, this is for a table. How do we go from a table to a function approximator, right? And so what you do in function approximator land is that you do like a tabular Bellman backup plus a projection. And so what I mean by that is that you can think of this term as like a tabular Bellman backup, which is saying that like in my current batch of things, right, I am going to have like a vector of things, right? These are just like S0 to like SK, where these are things in my batch, right? They don't have to cover all the states in the world. They're just like K different things in my batch. And then I'm going to do this like this is your Bellman backup. And this is going to give me a new vector of things, right? And then to get this to generalize beyond that, I have to like fit a function to these things that can like appropriately represent them in infinite dimensional space, right? And so I find this graphic kind of easy to understand. Well, I made it yesterday. Basically, these were your initial values, okay? These were your initial values, the ones that we did. Now, what you're going to do is you're going to do one step backup, which is you're going to add R to them, right? You're going to add R to them. It's going to like move the values, right? And then you're going to try and do like, you're going to solve this like regression problem. So it's like you had these values, you like back them up, right? Or whatever. And then you try to like fit the best possible function to them, right? And that's going to be a projection. So you can think of this as like, take all the things in your batch, back them up, right? And then you're going to try and find the best thing in your function class. Like this function class could be whatever you want. We're going to use neural net for a lot of it, but it could be a linear function approximator. It could be a polynomial, right? You're trying to find the best thing in your function class that like gets as close as possible to minimizing the error in all those random values. And so the way you're going to like go from our tabular proof to function approximation is you're going to take every element, back it up, and then try to fit a function that best regresses on all of them, right? And so whenever you see like an update like this, right, you could think of this as a tabular backup. You can think of this as a projection, right? So it's like tabular backup projection, tabular backup projection, tabular backup projection. So it's still a fixed point iteration procedure, but it is not like a gradient descent procedure. It's like do a tabular backup, project it onto the best possible function class, and then let's do the next tabular backup. The point is that the reason you have to do that projection in the first case, in the first place, is that you like will never get the same states again. Right? So like the problem if I just did tabular backups is what if I get a state over here? I'm screwed, right? Or what if I get a state over here? I'm screwed. And so you need to fit the best possible function to your tabular backup so that you can answer what the value function is going to be in new places, right? Okay. Does that make sense?
Just like further about it.
Yes, exactly. Just like you have a batch, you're just going to back up that batch and then run find the best thing that fits. Right? And you're going to repeat this over and over and over. So you're going to remember this is your tabular backup. This is your projection, right? You just iterate on this procedure. So all the things that I mentioned in terms of proof only really hold for a tabular backup. As soon as you do a projection, they may or may not hold. Okay? They may or may not hold, right? So let's see. For instance, we showed that our tabular backup was a contraction. So we said if we counted everything and we projected things, or we counted everything and then we backed it up, then it's going to be a contraction. So in a tabular space, it's going to be a contraction. But if you're in function approximation land, like because everything in between is determined by your function approximator, it may or may not be a contraction, right? And so in general, you can't say whether tabular backups plus projections are contractions. You can just say that tabular backups are contractions. Right? And so the reason it's hard to prove that these things converge is because it's like this thing converges, but as soon as you project it into function approximator land, it doesn't necessarily converge. There's like, you should look at some of Simon's work. It like answers a bunch of questions about when these things converge. You have some conditions, settlement completeness and such, but they basically try to talk about when these things converge, but they don't always converge. And they don't always converge because this thing is not always a contraction. Does that make sense? Yeah.
In practice, we actually use like that expected contraction.
Yes.
If there's theory that can fill that.
Like how sample inefficient it is? Or?
No, the true expectations.
Oh, yeah. Yeah, there's theory that talks about like how, like basically you can show like you want, like if you want this error to be really small, you need your function class to have a certain property, which is called Bellman completeness. And you can talk about like how many samples it takes to get this error under some epsilon. And that's going to like answer like how bad your approximation is with finite samples, right? And so if you're interested in this kind of thing, look up like Simon Du's work. I think he's excellent. And work on like Bellman completeness. And that'll help answer when this converges. Okay, so the point here to make is that we did this procedure, right? We did this procedure. It's like deviating from theory a little bit, but it like often works. This is the lesson to take from empirical machine learning work. But basically, you like do a tabular backup of the projection, you repeat that a bunch of times, and then you displace your sum of rewards by R plus gamma V minus. And that's going to lower variance, but it's still on policy. Okay, does that parse so far? Like, if you didn't take away anything from the last few slides, that's fine. Like, just remember that like Bellman backups are contractions in tabular space, and hence they will converge. But when you go to function approximation space, there may not be contractions, and hence they may not converge. Right? But they often do. That's fine. Okay, but really what we want to do, we talked about these two conditions. Right? We talked about lowering variance. We talked about going off policy. Right? And so what we want to do is we want to be able to use arbitrary data. And this could include data from past iterations, right? So far, every time you need to do this, you need data from pi, right? Which means you can only use your latest data. But we really want to be able to use off-policy data. So data from like even past iterations of running this thing. You also want to be able to use data from other tasks or other experiments or expert demonstrators or anything else, right? And so you want to be able to have a method that uses arbitrary data, not just data from pi. Yes. Okay. So before we get into that, let's take like a 2-minute break and we'll get into off policy. Sorry?
You look that tired.
You guys look a little tired. I'm a little tired.
Yeah. Yes.
The choice of reward function is very important.
No, because it cancels, right?
No. Like what I mean is like, because when we actually, when you go from tabular to approximated functions, you have to like.
Oh, sure. I think the choice of reward, the choice of dynamics, and the choice of policy are all important.
I guess then how do you make sure that you have like good reward function in the first place? In model.
Bit of I don't think we know the answer to that yet.
I see.
So I think it's like there's like one reason which is exploration, but this reason you're mentioning is not exploration, it's like approximability.
Yes.
I don't think it's very well understood. So yeah, it's a very good question. I don't know. You should find the answer. Yeah, tell me. That's a good question. No, nothing yet. I think I have to publish it. Maybe I graded everything, but huh? I left feedback on all. Everyone has submitted. So I think I just have to publish it. So I'll take a look. Okay, I'll publish it. I'll publish it.
What's the reason we're querying from projection?
Well, if you're querying from projection, it's because your data might not be the same, right? So, like in this setup, right? Like if you have, like this was your batch of current data, right? And now, because you're in an infinite dimensional space, you'll never get those things again, right? Or like, sorry, infinitesimal space, like as in you might get a new state right there, but it's not one of the states that I had before, right? So I need to like answer the value for this state, even though I've never seen it before, right? So it's like, imagine that I'm doing this like,
I thought we were using like state samples from the policy from before and then.
Right. Right, as in
addressing the-
what you're doing is you're saying, imagine that you had a batch, okay? So the batch had like S1, S2, S3 till S100, right? And now all of these got backed up to something. And we like, let's say we didn't do the projection, okay? Now what's going to happen is I get like S101, which is like not equal to any of these states in the next round of data collection. Right? So I ran my policy, it encountered a new state that it's never seen before. And if I don't do the projection, I don't know what the value function is for S101, right? Because it's like, this is an uncountable space. As in there's infinitely many states. And so unless I back it up into a function approximator, I cannot answer what S101 is. Like, I know how to answer these.
So we, as we keep sampling,
As
the
we keep-
tabular like grows.
It doesn't work. Yeah. So as in the tabular grows because you just like your data set grows. Right? And so the tabular grows, but you still might need to answer questions of things in between, right? And so unless you fit a function approximator, you can't answer those questions.
Yeah.
You can do things like nearest neighbors, like, or you can say that let's not do a projection with a neural network, let's just do nearest neighbors, right? But that's still a projection. So you're saying that like I query the Q function here, I just take the nearest neighbor from my set, or I take my Q function here, take the nearest neighbor from my set, but I still have to like do some sort of projection.
Yeah.
So
And for the neural network approximators, there's no extra regularization. It just like for like the in between, like the projection, just like.
often actually regularizers seem to help a lot. And so often you'll do some like smoothness or Lipschitz regularizers and they prevent it from going crazy.
Yeah,
And so they actually help.
I see. Okay.
All right. Yes. I was just saying I've created them all yesterday and I guess you can't see them yet. So I just need to publish them. I'll do that. Yeah. Thanks for bringing it up. All right, let's keep going. Okay, so we want to build algorithms for doing off-policy stuff. So we've been doing on-policy stuff all this time. And we want to build a method for doing off-policy stuff, right? So the trick is to go from Bellman backups on value functions to Bellman backups on Q functions. Yep. And so we're going to notice that Q functions have recursive structure as well. In that you can say that your Q function is R SDAT plus the expectation under phi of R of ST prime AT prime at ST plus 1 and AT plus 1 samples from phi. Right? So it's important that in your Q function, your first step is according to AT, not according to phi. Your first step is according to AT. And every step thereafter is according to phi. Right? And whereas in your value function, even your first step was according to phi. So the important thing that's going to let us be off policy is that your first step in your Q function is going to be inputted to your model. It's going to be AT, and it's not, it doesn't have to be from phi. Right? It can be, you can like query any action. It doesn't have to be. Let's just say, how good am I if I take an action AT and then follow policy phi, or the value function says, how good am I if I follow policy phi from state S? Okay, and so the Bellman equation for Q function looks very similar. So it's going to be Q pi SDAT is R of SDAT plus expectation of AT plus 1, or next state sample from B and SCAT, which is dynamics, right? And AT plus 1 sample from your policy phi theta. Right. So you're going to say that the important thing is that your action here, this action and this action can come from pi, this action can come from anywhere. Right. And so the important thing is that this action is coming from anywhere, this action is coming from pi, and so that's going to let us be off. Okay. I will get to that in a second, but the important thing to remember is Qs have one action that is different than every other action from pi. But graphically, it looks like that. You're still backing up values, but the important thing is that this AT and this AT plus 1 can come from different policies. And so let's kind of look at what the update looks like. But if AT and AT plus 1 can come from different policies, that means that you can estimate, you can construct a element update, which uses a different set of data than I in order to estimate. And so we'll look at that in a second, but that's the key point, right? Yeah.
The transition function is given.
You assume that you have samples from it. Like you assume that the off-policy model doesn't work if your dynamics change. So if your dynamics are stationary, you just assume that you have samples from it. But you don't assume that it's given in analytical form. Okay. And so what we're going to try and do is we're going to try and, let me kind of get to the objective. So you're going to try and solve an objective that looks like this. So it's going to say that you want to regress between Q pi SDAT and R SDAT plus Q pi phi hat ST plus 1 AT plus 1, right? So actually, let's go back one step. Maybe we can look at this thing a little more carefully to understand why this happens. But it's saying that, like, imagine you had a set of data. Okay, the set of data was SAS prime. For each SAS prime, what you can say is that I can stick in, and this was like from some policy pi beta, which is not equal to pi theta, right? So let's say it came from some behavior policy. That behavior policy was not equal to pi theta, right? What you're going to say is that because your first, because your first step can come from something different, your, like, this data will tell you S and A transitions to S prime, but like this A can go into here, and then your future Q is evaluated on A, which is sampled from pi theta at ST plus 1. So the point is that in the previous step, right, what we were doing is we're using a value function, which means you have to sample the first step from your policy, right? But here, what you can do is you can say, I'm going to sample the first step from a different policy, pi theta, right? So you're going to say S and A are going to come from some policy pi beta. It's going to transition to some S prime according to the dynamics. And then I'm going to sample an A prime from some different policy pi theta. And these two policies don't have to be the same, right? And so the nice part about this is you can think of this as like this transition tuple is just telling me what is the next state that I go to. That is like inherent to the dynamics of your system, right? So say, if I was at S, I took some action A, to come from any policy, it's going to go to S prime. And then to evaluate the future value under the policy you care about, which is pi theta, you sample the next action, not from pi theta, but from pi theta. And so the way you can think about it is like your data was sampled according to something, right? You like took one step, S and A took you to S prime. Your data took you like mostly here. But really what you want to do is you want to, and let's say you had a few samples here, but you really want to answer how good is a policy that really takes you like here, right? So in a value function, you can't do that because you always sample from your policy. In a Q function, you can do that because you can sample from a different policy, right? And so you can say that my transition will tell me to go here. No. My transition will tell me to go here. And then I can sample not A according to the policy from which the data was collected. Instead, I can sample A from the policy that I care about, right? And because your Q function can accept an action as an input, it will take the action not according to the data policy, but according to the policy that you care about. And when you repeat this over and over and over, you get evaluations for the policy that you care about, not the policy that the data was collected from, right? And so the point is that that first action being different allows you to like stick in action from a different policy at the next step. And if you can stick in actions from a different policy at the next step, then you can evaluate a different policy. Yes. So just to like, this is a little bit of a confusing concept, but like, remember that like this thing is taking a first action that is different from every other action after. So you're going to take the first step from pi beta, and then all the later steps from pi theta, right? And so, or like rather the first step S and A can be from pi beta, but like the data set really, all the data from pi beta just tells you what S, A, S prime transitions exist. And then to get everything in the future, you can sample A prime from whatever pi theta that you want, which is not equal to pi beta. Yeah. All right, does this make sense? Ish. Okay, so let's kind of look at how this is going to work. So just like we did with value learning, you're going to approximate Q with a like a neural network or something, right? You're going to have a function that takes an S and A and gives you a scalar. And what you can do is you can construct an objective that looks something like this. And so it's important to look at how this works, right? So SCAD plus 1 can be sampled from any data set. That data set does not need to, there's some conditions on it. It needs to have enough coverage. It needs to like have seen enough states and actions. You can't evaluate something that your data hasn't seen, but it doesn't have to be the same as pi theta, right? So the important thing is this whole procedure is going to give me Q pi theta using data which is not from pi theta, which is why it's off policy. Yeah.
So pi theta is no longer part of our data. It's not part of our data. It's purely implicit.
Yes.
This is
Exactly. And it's important that you need to be able to sample from pi theta.
right. You can run it forward if you wanted to, but you don't.
You don't have to, but what I mean is that it's important that when you sample the like next Q, you sample that action from pi theta. Right. So that is what makes it off policy. So it's important that you like have a policy that you know how to sample. So like what it means is that like the data tells me SA transition to S prime, and the policy tells me that at S prime, I'm going to take action A prime. And that A prime has to come from the policy.
That's big exhaustive.
Yes.
Trajectories. This is just like Q with one
Yeah,
value.
exactly. Right. And so the point here is that we're going to try and learn a Q phi path such that it matches our SCAT and expectation of AT plus 1 sample from pi theta of Q phi hat ST plus 1 AT plus 1. Yep.
I'm not sure this changed anything, but isn't the right hand side of the expectation just the value function of S2 plus 1 because it's the expectation of actions?
It's the value function.
So, I mean, does that simplify things at all? Because we just spent time like working with the value function.
It like the problem with the like it doesn't simplify things that much, as in like the value function like if you just did value updates, like the value update doesn't allow you to sample the first action differently, right? And so you can't actually, like you can like regress all of this onto a value function, right? But it doesn't really change what you need to do.
We spent the time before like showing like you can on policy run a value function. And then now after a little bit of that, you put it here and then train it how we're gonna do this.
Oh, sure. You can like initialize from a non-policy
Yeah,
thing.
this
So,
give you like a strong starting point to then learn off policy.
but you could just like do this whole thing off. Like you can, everything that you can do on policy encompasses, off policy encompasses on policy, right? So you don't need to do the on policy thing if you can just do the off policy thing, right? Because an on policy distribution is just one instance of an off policy, right? Yeah.
What are the difference between phi
And phi hat.
and then three?
Phi, sorry, could you repeat?
Phi and then theta
Yes.
and then phi hat.
Good question. Good question. So the Q function is parameterized by phi. So you're gonna have a neural net which takes in your Q. The parameters of it are phi. It's gonna take in S and A and give you a scalar. Right? Now you're gonna have another Q function which we'll call a target network, which I'll describe in a second. And that is gonna take in S and A and give you scale. Okay, this is phi, this is phi hat. And then you're gonna have a policy whose parameters are theta, which is gonna take an S and give you a distribution over actions. That is your policy, right? Like in policy grid, that is your policy. I mean, so the way that this algorithm is gonna work is that you're gonna like take a policy, run this update above to like evaluate it, and then you're gonna use that Q to like do policy improvement using policy grid. Right? So you're gonna like take a policy, run that a bunch of times, so you get a Q, until you get a Q. You're gonna use the Q to improve that policy. You get a better policy, you run it again. You get
Oh,
a-
okay.
and you repeat that. Yeah.
So how can you just sort of select this?
Which policy you're gonna sample from? Yeah, so the procedure we're gonna use, have it in the next slide, somewhere in here, sorry. So you're just gonna do an iterative procedure. So you're gonna start from some random policy. You're gonna collect a bunch of data. Then you're gonna like run that update on all the data that you've seen so far. You're gonna get a QPy, right? You're gonna update your policy. We'll talk about that in a second. You'll get a new policy, select some more data. Then you run your Bellman update on all the data you've seen thus far to get a better QPy, and then you update the policy over and over. So you start from like, essentially the way that it works is you start from pi naught, you collect some data. Data and pi naught give me QPy naught. QPy naught gives me like pi one. And then I collect some more data, and then I repeat, right? And so like I keep aggregating all that data into my big data store. Right, because it can now it can be off policy, so I don't need to just use my latest data. I can use all the data so far, and I just start from a random policy. I evaluate it, I improve it, I sample again, I evaluate it, I improve it, I sample again. So it's like policy gradients, but every time before, rather than using the current sum of the words, you like evaluate this Q function, and you use it for policy gradient, and then you update your policy, and that's the policy usage. Your first step is going to be on policy. Correct. Yes. Good. Sorry, can you repeat that? So when I say phi beta, I just mean like proper, like it's just like a big data set that just stores all the data you've seen so far. So let me, just to avoid confusion, let me go in steps till we get to the whole algorithm, and this will become a little more clear. Someone have another question? Okay, so let me go back to our update. So yeah, Andy just asked a good question, like what is the difference between phi and phi hat and theta, right? So theta is our policy. Phi hat is our, we'll call it target network, and phi is our Q network, right? So if you remember my my update from before with our value function, right? Like if you remember, I took this, I wrote it as a number, and then I like did regression with that number, I treated this as a number, I stopped the gradients through it, right? We took these things, we projected, treated as a number, did regression, only updating these values, and then you updated the targets again, right? And so the reason I've labeled this as phi and phi hat is that at this point, like phi hat is equal to phi, you're just gonna like stop the gradients through it. Right? It's like the same thing of like you're constructing targets on the right-hand side. You're taking every sample, you're constructing a target for it. And you're just like not going to take the gradients to the right-hand side, right? Because it's a fixed point iteration procedure, it's not a gradient ascent procedure. So you're gonna like, that's why that phi hat, when you optimize with respect to phi, you don't take gradients to that phi. Okay? So the way you implement in practice is that you like stop the gradient to that phi. Yeah. And so the reason it's phi and phi hat is the same reason we had before, where we construct targets, you treat them as numbers, you do regression, construct targets, treat them as numbers, do the regression. Is like you don't want to take the gradient through this side. We'll talk about why we don't do that in a second. But the way you're going to like implement this update is you're just going to sample S8 S prime from your data set. Then you're going to construct the like objective, which is QSA minus the reward at that transition. You're going to sample SAS prime R. Usually your replay buffer will have SAS prime R. Sample SAS prime R, you're going to say Q minus R plus Q by hat. So you don't take the gradient through it. At the next time step, SD plus 1, with actions AT plus 1, which are sampled from your policy. Right? So the important thing is that you have to sample actions from your policy, otherwise it's not going to be off policy. Right? And so like you just repeat this objective over and over and over. Like you just optimize this objective using the same procedure we did earlier, right? You're gonna like freeze phi hat for a while, solve this objective to get a phi, then you're gonna update phi hash to be the same as phi, and you're gonna repeat, right? So if you remember earlier, we had done this like yi is r plus v, right? And then we like said, okay, we're gonna take these as targets, and v phi minus y, we're gonna minimize with respect to phi, right? And then we like take our new v phi's and stick them in here, right? We're gonna do exactly the same thing. We're gonna say our new targets are r plus q SA, where this is coming from your policy phi theta. You're going to try and do, let's call these yi, right? You're going to try and do regression to yi for phi, right? You're going to try and find the phi that minimizes the distance to the yi. And then you're going to say, after a while, I'm just going to take these things, I'm going to update my yi's, and I'm going to repeat, right? So it's the same procedure. The only difference, you're going to do it on Q's rather than V's. And you're going to sample the actions from the policy. That's going to let you be off policy. And so you do the same procedure, you construct targets, use the targets for like minimizing a regression problem. Then you like construct new targets, and then you repeat, right? And so you're going to like iterate this procedure, same as we did in fixed point iteration for values. You're just going to do it, right? And this is like exactly the same objective as we, or like similar objective to what we did earlier. It's just on views rather than on these. Okay, does that make sense? Yeah.
Presumably there's a similar proof, but it doesn't have to say
Yeah.
that the same thing is contract.
Yes. The proof for Q learning is a little more complicated, but I think value iteration is easier. Yeah. No, it's like the saving here is that like in a value function, you are like by definition sampling your actions from your policy. And because you're allowing this queue to take an action from a different policy, I can still use the same data to learn it. I can use wrong data to learn Q, whereas I can't use wrong data to learn.
The action AT+1 is that.
That is something from the policy. The policy you want to evaluate, not the policy that collected.
Right, okay.
Right, so the important thing is like this is from the policy that you care about evaluating. So your data set, for instance, could be like all this internet data and like all my past iterates from pi 0, pi 1, pi whatever. And now I am at pi I, right? I want to evaluate pi I. So all of this data can go into sampling this thing, and pi I is going to sampling this thing. Right? That's the benefit here. And so importantly, like the nice part is that you can use all of this past data, whereas in none of the methods before you could do that.
can understand in a function approximation setting, despite the actual 80+1 that I actually take on policy, right? I actually never know the rewards that I'm going to get if I do that, take that action in the environment. Because I only have some other data set that I'm using.
So the data set has to have coverage, as in like you can't answer counterfactual questions. Like I can't say like I've never picked up a goat before, like what's going to happen, right? Like you have to have coverage, but the distribution can be different, right? So like for instance, like a lot of times when you like aggregate all your past data, you'll have coverage, but the thing you really want to query is not like all of the past data, right? You just want to query like your current pi, how good is it? But it's covered in the union of all the previous data, right? So a lot of times these off policy things that have a coverage assumption and like they don't work without coverage. Any other questions?
Oh, sorry. But like essentially you have to have the 3 neural nets. Have 3 neural nets and 5.
That's right. So this looks like this is kind of what I've been alluding to the whole time. It's like looks like gradient descent, right? Like this looks like I can just optimize the gradient, but it's not quite gradient descent because you keep changing your objective, right? So you're gonna run this for a while, and then you're gonna like swap out pi hat to the latest value of pi. You're gonna run this for a while, swap out pi hat to the latest value of pi. So it's not gradient descent on a cohesive objective, right? And so what it's doing is this fixed point detection procedure, which is not gradient descent. Right? And so there's like a bunch of reasons for that. I'm just going to skip it for the sake of time, but they're in my slides. Take a look. Yeah. Yeah. In practice, often what you do is like you do this like exponential moving average. So sorry. You like don't move pi hat to phi completely. What you do is you like move, like you take a moving average of pi hat in the latest phi with some like whatever weighting parameters. And so you do that like every 5 or 6 gradient steps, you move it a little bit. That tends to work a lot better. Okay, so we have like 7 minutes. So let's try to close the loop on what the whole algorithm looks like, right? So far we've talked about policy evaluation. So we've said the loop, as I was just talking about, has like pi 0. Pi 0 is going to collect some data. Data and pi 0 are going to be used to get like q pi 0. Q pi 0 and pi 0 together are going to be used to update this to pi 1, right? And then pi 1 is again going to collect some data. This data and this data together are going to give me q pi 1. This is going to give me pi 2. Repeat, right? And so the next step we need we've discussed how to do this step, right? That is like the Bellman update we just talked about. You just like minimize this Bellman error, you repeat, you get q pi 0. And it's off policy and it's low variance, it's good. Now, how do we actually improve our policies, right? So I now have q pi 0. How do I improve my policy? So I know q pi 0. What do I do with it? I'm sorry? Do you say take the best action? Yeah, it's basically that, but you do it with policy gradient. So like what you can do is that you can like if you remember our policy gradient objective, it has this like grad log pi term. You can like replace the sum of rewards now with your q. And that earlier, if you remember, we were doing r plus gamma v minus v. Now you can replace that whole r plus gamma v thing with q, right? And that's going to be lower variance and it's going to be off policy, right? So it has all the benefits we want. And so the policy improvement objective, you can often write like this. You can write it as you're saying sample states from your data set, sample actions from your policy by theta, and you want to maximize the q value of that action at that state, right? And now if we like, I'm not going to go through the math again, but if you use the reinforced trick, you can feel free, don't worry. If you use the reinforced trick, you can rewrite this as expectation SD A from pi theta of grad log pi theta times q pi, right? Just like the same thing we did in policy gradient. So if you want to maximize objectives, just do the multiply divide trick. You can just rewrite this as is basically policy gradient, but you're just replacing the sum of rewards with a Q, right? And so that's the basic objective you want to maximize in your policy improvement step. And so essentially it gives you lower grades compared to policy grades and allows you to do it off policy. Okay? So that kind of closes the loop, in that we did policy gradient was good. There's high variance on policy. Now we have something that's low variance off policy. Better, right? Okay. We will go through the rest next time, but thanks. And I should have feedback for all of you today. The proposal is very good. I got your proposal. I will read it. Yeah. Yeah, I'll just email you.